Hello everyone, welcome to the last class on advanced characterization techniques. So in the course of this series, we have gone through the basics of X-ray diffraction and scattering. We have studied small angle X-ray scattering as well as grazing incidence small angle X-ray scattering. Then we also studied electron diffraction, and finally we studied some spectroscopic technique using X-rays. In the last class, we had studied a few things about neutrons, and in the final lecture today, we are going to extend what all we studied about neutrons to a technique which we had studied earlier, that is small angle scattering. In the earlier classes, we had gone through small angle X-ray scattering, and we had also realized what are the advantages of using neutrons, and therefore in the present class, we are going to extend the same geometry or the same concept of small angle scattering to neutron scattering. So, as we had discussed earlier, that interaction of photons with matter can lead to scattering or as well as diffraction. Now, scattering of X-rays is essentially from electrons, right? And we had seen earlier in the last class that scattering of neutrons is from the nucleus. We had also seen, now this slide is almost borrowed from what I had shown you during small angle X-ray scattering, that this is what is your diffraction, where your incident X-rays or for that matter neutrons interact with the lattice planes, and which occurs at a very small level, right, of the order of the wavelength of the incident X-rays or neutron. While when we talk about scattering, scattering occurs at a higher length scale, right, and small angle scattering most of the times is from interfaces. Now, this is what we had seen earlier also, and the same concept remains valid even for neutron scattering. However, I hope you remember that in the last class we had seen that depending on the energy, we can get neutrons of very different wavelengths, right, and therefore we can see a variety of objects. Theoretically, I hope you appreciate that we can see a lot of a wide range of objects using neutron diffraction compared to X-ray diffraction. This is precisely because we have neutrons in the energy range, in a wide energy range, which in turn gives us a wide wavelength regime. Having said that, generally most of the neutron scattering or small angle neutron scattering also has the same size regime as that of small angle X-ray scattering. As we had seen earlier, that at the very small length scale, right, we have very large angle, and this constitutes the normal diffraction. As we have for X-ray, we have similar condition for neutron diffraction also. However, at large length scales, we get smaller angle. However, I am now going to say something which may kind of surprise you. We are talking about small angle neutron scattering, and in the last class or in the couple of classes before, we talked about small angle X-ray scattering. However, this term small angle within quotes is actually a misnomer, because if at all we are having a change in wavelength, the angle at which we are getting scattering is going to change, and this is particularly valid for neutrons, where we can get a wide variety of wavelengths. Therefore, the correct term should be actually low Q or low K diffraction for what we term as small angle scattering, and normal wide angle scattering can be referred to as high Q diffraction or scattering. So, this is just the kind of terminology that has kind of stuck with the technique, but I hope you appreciate that in small angle scattering, we are mostly dealing with what is happening at very low Q values, while at higher Q values or K values, we deal with wide angle X-ray scattering, which is a conventional intensity versus 2 theta plot, right. So, let us move over from there, and I would just like to remind you again that the small angle neutron scattering theory is exactly similar to that of small angle X-ray scattering theory, and for most practical applications, we are having the same size regime as we have for small angle X-ray scattering. But the big advantage that small angle neutron scattering offers because of the use of neutrons is that we can penetrate deeper. We can penetrate deeper within containers, right, which are made of metallic materials and containing various soft matter, right, like your polymers, and what all things are happening to it as a function of flow or applied stress, and therefore we can study the rheological as well as flow behavior of the soft matter using small angle neutron scattering. At the same time, a big advantage that neutrons offer over X-rays is their ability to detect light elements, right. So, particularly this is very, very important when it comes to biological materials, right, and therefore small angle neutron scattering has extensive application in biological, chemical as well as ferrofluids materials. Here again, for ferrofluids, you know that neutrons are sensitive to the magnetic moment and therefore can give us information about the magnetic structure. So, all this information is obtained using small angle neutron scattering, which is generally not obtained in small angle X-ray scattering. One more important thing that we had stressed in the last class was about the ability of neutrons to separate between isotopes. Now, this ability of neutrons can be used to get better contrast. We will talk about this in the couple of slides, but I hope you appreciate that the advantages of neutrons over X-rays can be exploited in this technique to get relevant information from our experiment. So, just to revise and put things in perspective, I hope you remember that we had this sample on which whether neutrons or electrons are getting kind of they are incident, and we see that it scatters the incident beam, right. And you see if Ki is your incident beam wave vector and Kf is your scattered wave vector, we had defined our scattered wave vector q as q is equal to 4 pi sin theta by lambda, right, and the overall intensity that we got on the screen or our detector is nothing but phi is nothing but the distribution of particles, and pq is nothing but the form factor, right. If you remember, like this contribution comes from all the atoms that constitute our particle, and the SQ is nothing but the structure factor, right, and the structure factor comes because of the arrangement of these particles. So, this theory is exactly similar to that of small angle X-ray scattering. So, again if you remember, we had two regimes, right, we had the Guiner regime and the Porot regime. The Guiner regime was valid at Q max Rg less than or equal to 1, this product Q max is nothing but your wave vector, right, into Rg, where Rg is the radius of gyration, which was for sphere as square root of 5 by 3 times the radius of the sphere. So, it gives you the slope of this line minus Rg square by 3 if you plot ln of intensity versus Q square. This is our Guiner regime. However, at high Q, now mind you, this higher Q is not the high Q regime which corresponds to the wide angle scattering, but at high Q regime we see that ln of I is proportional to Q power minus 4, and we see that from this information about what all slope we can get information about the shape of the particle, right. This is what we did in small angle X-ray scattering. Now, the same concept can be borrowed and applied directly to small angle neutron scattering. Having said that, let us try to see one particular thing or rather one particular concept that is not seen or not quite prominent in X-rays, and that is the ability to separate between the isotopes. But before we go there, let us kind of rebuild and revise how actually scattering occurs. So, all of us are aware that any particle, if we take, the particles are characterized by a scattering density, right, which is rho of r. Now, this rho of r or the density of scattering depends on what all atoms are there, right. So, the particle which comprises of atoms. So, the scattering tendency of the particle is nothing but the summation of scattering tendency or scattering ability of all these atoms, right. So, therefore, you see that your scattering density rho of r is nothing but summation B I. Now, it has to be averaged over the volume of the particle, and therefore, the scattering density is nothing but summation B I over rho. Now, these particles are not standing alone. Instead, most of the cases these particles are there in a solution, right. So, we also have to assume like what is the density of the solvent under consideration. So, let it be say rho 0. So, if at all our neutrons were to pass through a solution comprising of a solvent of scattering density rho 0 and particle with scattering density rho of r, where r is a function of the location of the particle, the intensity that we get can be given by this formula. Here, mind you, look what we are having over here. So, this is the difference in the scattering density of the particle and the solvent, and this is what gives us the contrast. So, this is the resultant scattering density. Here again, the value of q which we had seen, the wave vector is nothing but 4 pi sin theta by lambda, right, and you see this exponential term and you see it is proportional to d cube r, right, and the whole thing square. So, this is again very similar to our structure factor, right, and this also accounts for the size part. So, moving on, the form factor is related, as we had seen in case of small angle X-ray scattering also, to the scattering density. Therefore, our P of q is nothing but f of q square. Now, this is very similar to what we got in case of diffraction, right. The intensity that we get is directly proportional to the square of the amplitude, right. The same over here, and this f of q is nothing but the difference in the scattering density of the particle and the solution, right, or the solvent. Okay. So, this is the f of q term. Similarly, if you remember, the structure factor which we had calculated in small angle X-ray scattering remains the same when it comes to small angle neutron scattering, and it has to do with the spatial position of the particles. So, see, we have a form factor which depends on the size and shape of the particle, while the structure factor is decides the, or rather is dependent on the spatial position of the particles. And here you can see that r alpha and r beta are nothing but are nothing but the spatial coordinates of the two particles. So, and there is a big summation sign and everything is averaged for the particle under consideration. Okay. So, now let us move ahead. So, you see that we do have a excess amplitude or contrast length. So, this is very important. So, this is what we want to maximize. In small angle X-ray scattering, in order to get an estimate of the shape as well as size of the particle in the solution, we need to maximize the contrast, right, and this is what is the contrast, right. So, I would like to remind you that this is your scattering ability was nothing but summation B I over V, okay, isn't it? Rho is equal to summation B I over V into d cube and r. So, what we get over here is actually a contrast length, and this is the term on your right hand side which we want to maximize. Now, in order to get sufficient signal, sufficient number of particles must be there, right. Like if the particle size is very small, you should have sufficient number of these particles, very small particles in your solution, so that you get good enough signal, and from this signal you can decipher the size, shape as well as distribution of these particles in the solvent. And in order to do this, you have to make certain approximations, and we assume that all particles should be identical, right. Their orientation is random. We have lower concentration, so that there is no interference of scattering caused from one particle with that of caused by the other particle. Another important thing is we ideally like a two component system. So, you have a solvent and your particle, right, which may be a macromolecule. You do not like any interaction taking between these two and having the presence of third phase. So, in this case the situation is very clean and you can do very easy analysis of your sample and get information about the size, shape as well as distribution of the particle under consideration. So, before I proceed, you see here the contrast term, the contrast length that I have shown over here. We have just noted down for different nucleus. Mind you, this contrast term is for nucleus. I had mentioned that it is for different atoms, but mind you, our neutrons, we should remember that neutrons do not interact with the, means they do interact with the atom, but they do not interact with the electron cloud of the atom, but with the nucleus of the atom. And you see, for light elements we do have different values and very good values, light as well as heavy elements. Another important thing is, look what we are having here, hydrogen and deuterium, and as I had mentioned that they have different scattering cross section. Here again we see that they have different scattering length. Not only the magnitude is different, but also their sign is different, and this is where lies the biggest advantage of neutron diffraction. You know that most of the biological systems comprises of hydrogen. So, many a times we can play and replace hydrogen with deuterium and try to get or improve the contrast. Now, this is something that is very difficult to do using small angle, or rather it should be not possible, it is not possible in small angle X-ray scattering. Okay, so again let us go back and try to work on this macromolecule solvent stuff. So, scattering due to solvent and macromolecule needs to be separated, right? Like at the end of the day we are getting signal from both the solvent as well as the macromolecule that we are studying. So, we need the overall scattering is essentially rho of r is rho v plus rho f r, where rho v is your average scattering density of the particle. Now, this comes from the particle, while rho f of r comes from the fluctuation about this mean. Now, this is caused essentially because of the interaction of the particle with the solvent, and therefore, the scattered intensity, I hope you appreciate, can be given as nothing but rho v, which you have over here, minus rho 0 square I v q plus rho v minus rho 0 I v f q and plus I f q term. So, this fluctuation term also plays a very important role in deciding the intensity, right, and this is where it comes, the overall intensity. So, if at all we have to see contrast, we have to change this fluctuation, right, and this will happen, how this will happen? Again, this will happen by changing the interaction between the solvent and the macromolecule. So, that is what I mean, that we can modify rho 0 by mixing H2O or what, or D2O, deuterium oxide, right. So, if you have a particular solvent, you can add water in it, right, or you add heavy water, that is D2O in it. Now, this will ensure that our IVQ as well as IFQ can be determined from the contrast series, right, like in one case you have only your solvent and macromolecule, in the other case you add water, and in the other case you add D2O, and then you compare, right. So, your IV, let us go back and see what is your IV. IV is the scattering density of the means the intensity due to scattering by the particle, while IF is actually due to the fluctuation part, right, and the fluctuation is going to change as we change the solvent. So, it is a bit mathematically involved, but I hope you appreciate by changing different solvents we can get some information. Having said that, there is however two problems. The first problem is that there is perturbation in the solvent at the interface, like if we change the solvent, there is almost always some perturbation. So, the perturbation level may change. At the same time, what may happen, like if you are changing something with say hydrogen, right, if you are just in a solvent, if you are putting water, what may happen is the hydrogen ion which is in your macromolecule may get exchanged with the water, the hydrogen ion in the water that you are adding. Things will get even more problematic if your hydrogen is replaced with deuterium. But having said that, it is still the aforementioned technique of changing the contrast by adding hydrogen and the water and D2O is quite valid. And as we move ahead, we again come across this intensity versus intensity as a function of Q term, which is nothing but I0 plus we see here your radius of gyration Q square by 3 term. Now, this is again similar to what we had got using small angle X-ray scattering. The only difference that we have over here is that in this case again your scattering ability or scattering density is a function of you see for your particle, okay, as well as, but you have to subtract it from that of the solvent. I am invariably using particle and macromolecule as meaning the same, though you should keep in mind that these macromolecules are pretty large and they can agglomerate and form a small particle. Okay. So, this is what we talked about was actually what is known as contrast variation. So, we know that compounds with close scattering length give low contrast. That is because if the two atoms are having the same, two elements are having the same scattering ability, we cannot differentiate between the scattering due to the individual element. However, small angle neutron scattering offers improvement in contrast by isotope substitution, right. So, instead of if you are having hydrogen, why do not you put deuterium, right. If you want to look for say a particular isotope of nitrogen, right, instead of N14 you substitute it with N15, right. So, this gives us the possibility of erasing the scattering from solvent by using normal and deuterated solvent. This means you take a solvent which is normal, right, and then in one which contains water, and in the other case you put heavy water and try to match how the contrast is changing. And if you do it that way, what we can do is, see, the whole idea is if we have more than one type of particle, right, or more than one type of macromolecule, what we can do is we can play with the elements and we can glow. So, it's just like if the entire wall is painted in white, you paint the region of interest in black. So, there is a lot of contrast, and if you want to see the outer part, what you do is the black region is painted in white and the rest of the region covers into black. This is what has been shown over here. So, you see here what we do is when you have two entities, right, you have a rho 1 and rho 2. So, these are two particles, right. So, now what we do is we do contrast matching. So, in contrast matching what actually happens is we look at rho 2, right, the particle 2, and make its contrast similar to that with that of solvent. So, what actually happens? We are not able to differentiate between particle 2 and the solvent, but this gives us the maximum contrast for particle 1, right. So, you can now very clearly see the particle 1 over here, fine. Now, what about particle 2? Well, we play the same trick. Now, instead of matching the scattering ability of the solvent with that of particle 2, we match it with that of particle 1. So, now particle 1 is invisible and we see the contrast only of particle 2. That is great, because using these two techniques one after the other, we have got information not only about particle 1, but also about particle 2, which means we have been able to differentiate between two species which have very close scattering length or scattering ability. So, you see how by intelligently doing contrast matching, we can get information and separate out two species which are having very close scattering tendency. Let me remind you that this can be done only in small angle neutron scattering because of the sensitivity of neutrons to differentiate between the isotopes of the same elements. So, this is one of the biggest advantage of going for small angle neutron scattering. Just to give you some kind of feel about where all we can do use small angle neutron scattering, I have cited a few examples. I won't go back and kind of repeat the same things that we did using small angle X-ray scattering, because with small angle neutron scattering we can do all the things that we can do using small angle X-ray scattering. And therefore, in the next couple of slides I am going to show you certain things which we can do only with small angle neutron scattering, right. So, if you remember, small angle X-ray scattering, or for that matter any X-ray scattering or diffraction experiments is always limited by the penetration depth of X-rays. While if you want to study flow behavior, right, of polymeric hydrogels, polymers, or polymer composites, polymer nanoclay composites, well, there is no way, like we have to apply stresses on it, right, or to make the polymer flow. Now, how do we do that? Well, we need containers, and that is what has been shown over here, the common coiter flow cell geometry as well as the cross section of common flow which are used in small angle neutron scattering environment. Now, keep this thing in mind, like like all these containers contain our polymer or hydrogel of interest, and we are going to apply stresses on it, right, shear stress, or to see how they are flow, we are going to actually squeeze in the material into these cavities. Now, how do we get signal, and how do we see how the structure is evolving as a function of, say, stress or flow? Remember, in order to actually get some information, our probe has to have the ability to pass through these containers and gather important information from the polymer or hydrogel under consideration. Now, this is absolutely impossible with small angle X-ray scattering, right. Even if we are using a synchrotron, the synchrotron radiation will not penetrate through these containers, and we will not get good signal. However, small angle neutron scattering, due to its high penetration depth, can give us some signal, and we can really study in situ the flow behavior, how the rearrangement of the particles, right, of the particles is taking place, or the nanoclay polymer composite, how the flow behavior as well as the reorientation can be easily studied using small angle neutron scattering. This is what has been shown over here, and you see here we have a biopolymer that was subjected to a shear strain of 145%, and this is how the pattern goes. You see, we do see some kind of an elongation over here, right, and what all information we have, this is the experimental part, we can incorporate, again go back and kind of simulate it and get this value which has been shown over here. Now, this is done using, again, commercially available softwares, or which are available at the neutron sources, various neutron sources in the world, and are very similar to the softwares that we use for small angle X-ray scattering. But having said that, the input that we are taking, one is your structure factor, and the other one, and most importantly, is our form factor. So, you see, we can get very nice information from the simulations, and we can predict how the particles have sheared as a function of strain. Not only that, we can also get the annular intensity average, and this is what been plotted over here, and also the sector average 1D scattering, which clearly shows that there is a difference in the scattering tendency of the particles perpendicular and parallel to the direction of straining, right. And here again we see what is very important, that there is indeed some reorientation of phases or particles in the biopolymer, right. So, you see like how we can use this and get information during in situ experiments, right, as a function of stress or flow behavior in polymers using small angle neutron scattering. Now, as I had mentioned, and as we also appreciated in the last class, that small angle X-ray means X-ray scattering and neutron scattering, or for that matter X-ray and neutron, can be used as complementary sources. So, here I am going to present a small example from a very old paper which is on silicon carbon nitrogen ceramics, and here both small angle X-ray scattering and small angle neutron scattering were used to actually characterize the material. So, these composites were prepared using pyrolysis of polysilyl carbodimide precursor at 1373 K to obtain silicon 24.4, carbon 42.4, nitrogen 33.2 ceramic. Now, these ceramics were amorphous up to 1673, that is 1400 degree centigrade, and here you see after annealing at 1400 degree centigrade we do get some peaks indicating the crystalline nature, okay. But below this temperature it is absolutely amorphous, but this is about wide angle X-ray scattering. Now, let us go and look at what happens in small angle scattering. So, on my left hand side I have the small angle X-ray scattering data, and on my right hand side I have my small angle neutron scattering data. Here again you see what we have, you see here 15N. So, here we have substituted, right, the nitrogen with its isotope, while here we have the native nitrogen, right, the native nitrogen. So, now let us compare the 1101 sample with 15N and the native N. Now, you see the 1101 is comprising of this tile over here, and you see where it goes. So, it goes over here somewhere, right. So, it is here, and the 1100 with the native nitrogen is a triangle, and you see where it goes. Oh, it goes over here. So, oh my god, we do have a difference, right. Theoretically, we were not supposed to have this difference, isn't it, because as we know, X-ray scattering is not sensitive to isotopes. However, this may be an exception, and this can be attributed to some problem during the processing. However, if you go back and look at the silicon carbide SiC with N native sintered at rather annealed at 1300 degrees centigrade, you see that it goes somewhere over here, right. This one, right. So, we see that here in this region there is almost a bit of match. So, let us assume that there is not much of a difference, right. And here again one point that I would like to emphasize is that though we talked about the difference between 1100 15N and native N, you see the almost behavior, right. This region it is almost parallel, right. So, you remember at very low K, if you are getting a parallel region, this corresponds to what? Well, this corresponds to, in this region, well, let us not talk about it, but it corresponds to the porod regime. Mind you, this is in negative, right. So, now if you go to the small angle neutron scattering, so let us look at 1300 degree centigrade curve. So, you have these squares which are over here, and here once you go, you see with the native nitrogen, right. So, this you see there is a huge bit of contrast, right. You see huge bit of contrast. So, where here is see lot of contrast, right. In fact, it is characteristically different, right. Once you have a native nitrogen, and here where you have the isotope, right. So, you see how much contrast we get using small angle neutron scattering. We saw that increase in temperature like led to the signal shift at lower H values. Now, this H is similar to Q or K that we had used. Now, even then at low K, right, or low H, we saw a linear behavior which is similar to the porod regime. Now, here you see, here we do not see that, right. So, you see the contrast. So, we are getting different information, right, from these two scans, though the range of the Q is same. So, see with small angle X-ray scattering, this is more of a linear log straight line. This is the slope will be about minus q to the power minus 4, right. So, around minus 4. So, actually this indicates the porod regime. So, here you see we see a nice porod regime, right, while here no porod regime is valid. So, you see depending on the wavelength and the character, whether you are using X-ray or neutron, we can get different regime. So, I just wanted to emphasize that we can't just blindly take the entire theory of small angle X-ray scattering and extend it to neutron scattering, and there indeed are differences, right. And here again we saw that isotope substitution gave very much, it gave quite a bit of contrast, a characteristic difference in small angle neutron scattering, right. So, this is how our study should aim, right, like you start with normal wide angle X-ray diffraction, and then you can do small angle X-ray as well as small angle neutron scattering. I am not going to go in details of this particular observation, but let us go ahead and look at one of the best advantage of neutrons, that is its ability to separate to get information about the magnetic structure. So, this example from a paper by Kopitsa et al., what we have done is there is iron manganese alloy, right, which has shape memory effect, right. So, that they remember once you change it as a function of stress and go from austenite one phase to other phase, they remember its shape. So, we used polarized neutrons in transmission mode, right, and I have not given the details, but in this case these are nice metallic materials, right. So, we instead of having a suspension, these were rolled plates of about 3 millimeter thickness, right. Now, you cannot imagine even synchrotron light to pass through 3 millimeters of iron manganese alloys, right, a sheet of iron manganese alloys which is about 3 millimeter thick. Even if the synchrotron radiation can penetrate, the signal will be very weak. However, neutrons can easily penetrate, and by monitoring the transmission signal, we can see that there was very small, they were able to see that there is very small scattering, which essentially indicated that there is low magnetic heterogeneity. Not only that, they also added carbon and nitrogen. Again, you can add directly or you can add their respective isotopes. So, you can add carbon 12 or carbon 14 or nitrogen 14 and nitrogen 15. However, this study they have not done, but you always have this option to maximize the contrast, and this is what has been shown over here. So, you see that the momentum dependence on intensity. So, this is our momentum transfer or Q of sands for silica doped iron manganese alloys. You see that the difference in intensities of scattering is due to because of carbon and nitrogen. So, this way we can study what happens due to addition of trace elements or interstitial elements on the overall shape memory effect, which has tremendous metallurgical as well as mechanical applications, right. So, again using only, and this can be done only using small angle neutron scattering, because we cannot get any information about the magnetic structure using X-ray scattering. So, to summarize, I hope you appreciate that small angle neutron scattering offers us a very powerful tool to study objects between 1 to 100 nanometers. It can be used, or rather it is used widely for several applications in the field of biology, chemistry, polymers as well as ferrofluids. The most important advantage is the contrast variation method for analysis of density in samples containing more than one compound. So, we can get different materials, right, different kind of phases which are present, right, in the same material. We are able to separate them in a much better way using small angle neutron scattering. And this aspect which I have not touched about, but as we already know, there are very good softwares, right, which are available for analyzing small angle X-ray scattering as well as small angle neutron scattering data, and we can reconstruct the size, shape as well as distribution of the particle under consideration. With small angle neutron scattering, we can also use to get information about the size, shape and distribution of the the macromolecule, which are of the order of, which fall in the same size regime. So, with this we come to the end of this module. Having said that, I hope I have been able to show you give you a glimpse of the entire spectrum of advanced characterization technique that use diffraction, scattering as well as spectroscopy principles. The major aim of this module was to just expose you to all these techniques, so that you become aware. I have not really gone into greater details, and there are plenty of texts available on these techniques. I therefore request you to go through the text which will be shown, which is on the website, where you can see what all textbooks can be offered. Having said that, let me remind you that all these techniques what we have used are very much dependent on the instruments that we are having, and therefore, the best information can be obtained at the facility which offers all these techniques. So, the main point is, if at all you are going to carry out say synchrotron diffraction or scattering experiment or neutron diffraction or neutron scattering experiments, it is always suggested to spend some time at that particular facility and carry out your experiments. With this, I will wish you all the best for your advanced characterization techniques, which you will probably find use at some time in your academic career. Thank you.